features that have apparently been discarded in the literature, and we revisited these things, especially removing one approximation that has been very popular, that is called the Boussinesq approximation. Okay, so we have heard yesterday in 2 talks using this approximation, and we are taking that into account. So we are not taking the Boussinesq approximation, and we'll see what will happen if we don't take that thing into account. And Holmboe instability, the name is after Holmboe, and these features that are there in the picture are 2 counter-propagating waves, okay, unstable waves, and that are named after him as Holmboe waves, okay? So the outline of my talk will be introducing first 2 different mechanisms for instability. One, Kelvin-Helmholtz instability, everyone knows here. Holmboe instability is probably not many of you know, but I will introduce it. So I will see how linear stability analysis can be used to understand this phenomenon. I will present the Holmboe's result from '62, and we'll see why it took more than 30 years to find this experimentally. Okay, so this was predicted in '62 theoretically using a very, very, very simple model, and it took more than 30 years to see it in a lab. Okay, and we'll see what really happens when you go beyond the Boussinesq approximation. Okay, so the Kelvin-Helmholtz instability. So this picture is very famous. This was took from the paper by Thorpe in '68, where you actually see a tube that is filled with 2 layers, okay, different constant densities, and you just tilt it, and immediately you see a watch there, a chronograph, and it's taking, after some time, you will see these vertical structures, these things, these rolls are building up, and after a point, it breaks into turbulence. So these things can always be seen when the thickness of the density transition layer is comparable to the shear layer thickness, okay? And what you can actually see is that the billows that are there in the picture are traveling at approximately the average velocity between the layers. Okay. So the question is, what happens when the density transition layer is much thinner than the shear layer? And what Holmboe predicted is that a second mode of instability should be present. Okay? And how this manifests? Well, it manifests by 2 trains of counter-propagating waves of equal strength. And these waves here, okay, this is actually an experimental data, okay? This is really a picture from a lab. And this is from 2010. Okay, so the numerical evidence for such waves have been there since '72, Hazel, Smith, and Peltier, but, no signs of its existence were actually found. So we see that this didn't happen because of the lack of experiments. So many people were trying to find those, but they were not successful. So none of these experiments were actually conclusive. They were not able to find it. But finally, in '96, Zhu and Lawrence, using exchange flows, they were able to see these counter-propagating waves. Okay? And this is, experiments versus numeric simulations. And you see that these things from there, this is the time evolving, okay, and they will meet. Okay, and this is the numerics. Okay, so how to understand this? Well, basically we consider the undisturbed profiles for the background velocity, capital U, density stratification rho that only depends on the vertical coordinate, okay? We'll reduce the study to the 2 dimensions, so there is only x and z component, okay? And since we are in 2 dimensions, we can introduce a stream function that is phi. And here, primes means derivative with respect to the vertical coordinate. And this is what we have, okay? So linearizing the other equations around this equilibrium will give you this governing equation, okay? So phi is the stream function, rho is the density stratification, u is the background velocity, and c is the phase velocity, and k the wave number. Okay, very well. And the Boussinesq approximation is when you consider that this ratio is really small, and this is of the same order, inverse order of this one. So which means, basically, roughly speaking, that whenever you see rho prime over rho, you just drop it. And you only keep the one that is multiplied by g, okay, over u minus c squared. Okay, and if you do this, taking into account the Boussinesq approximation, from linearized Euler equations, you go down to what is called the Taylor-Goldstein equation, okay, where here n is the square of the Rumsweiss-Halle frequency. Okay, so this is an approximate model, okay? And furthermore, you can actually say more. You can say, well, let me say that rho is actually a small deviation of a constant state, rho naught. Okay, in that case, you should not write this equation as it is there, but more like this. So you replace your buoyance frequency by this expression. So now it's not a rho bar over rho, it's rho naught here, okay? And most of results that we find in literature, when they say Taylor-Goldstein equation, they are actually using this one, okay? Okay, so let's simplify even further the problem and say the following. So we have these undisturbed profiles for the background velocity and density stratification, and we are approximating by piecewise linear functions. For example, the u could be approximated by constant, linear, constant, and let's say that the density has a very sharp transition, and we could say constant, constant, okay? Well, if we do that, you'll see that actually those governing equations simplify to this very, very simple equation, okay? So in the regions where rho is constant and u double prime is equal 0, you just have to solve this. And if you want to find the dispersion relation, well, just impose jump conditions at each surface of discontinuity. So we have just to be careful in prescribing these, because, for example, if you are using linearized Euler equation, you should be using these jump conditions. But instead, if you are using the Taylor-Goldstein equation, I'm writing here modified because I'm replacing n by n naught, okay? So I'm considering that rho is a small deviation of a constant state. So you see that this jump condition is not exactly the same as this one, okay? Okay, let's see how these things compare. So I will assume the undisturbed profiles for u and rho as given by Holmboe. So what he did is the following. Constant, linear constant for the background velocity, and assume that the density is constant, constant. Okay, and it seems more. This is, you will have to imagine if there is an inflection point for the background velocity, you will align, I will call that inflection point placed at z equals 0, and this will be exactly my interface for the two layers. Okay, so I will put this aligned with this. If I do that, and, well, write everything in non-dimensional variables, I will introduce the Richardson number, okay, where epsilon here is just the density increment to move from one layer to the other, okay? And if I do this, well, so you will just have to solve phi double prime minus k squared phi equals 0, submit it to the jump conditions. And this gives you exactly this dispersion relation, which is very particular because, for example, these A1 and A3 are proportional to this density increment, okay? And because they are proportional, well, we could say the following. Well, instead of working with a quartic, let's just work with the biquadratic form, which is easier to solve, right? Okay. And this is actually with what people refer as the Boussinesq limit, okay? So you'll take the limit where epsilon goes to 0, okay, so in order to these guys to go away, to have a biquadratic form, but being careful that j still remains finite, okay? I'm not throwing out the j, okay? So it's not just putting epsilon equals 0. That doesn't work. It's a special limit. So if you do that we call the Boussinesq limit, you get exactly this eigenvalue equation. Well, since it's a biquadratic form, instabilities have a very special structure, since we have what we call symmetric instabilities. So whenever c is the wave velocity of an unstable mode, there exists an unstable mode with velocity minus c conjugate, okay? And this is exactly what Holmboe did. He just looked at this special limit, okay? And this is the stability diagram. So here you have the Richardson number. Here this is the wavelength, non-dimensional, of course. And what you see is this is stable, this shaded region, and the white is unstable, okay? And if you zoom out here, this region, you actually realize that there are two distinct mechanisms here. There is one region 1 where all this is a quartic, okay? And all the solutions of this quartic or biquadratic are of this form, plus minus ICI plus and plus minus ICI minus. And when you move to this second region, suddenly things change. So you have now 4 complex solutions, but with this form. So that this is moving. There is one unstable mode with phase velocity CR, and one other with minus CR. So they are counter-propagating, okay? And this is what we called the Holmboe mode, and this is the, Kelvin-Helmholtz mode, and this is the Holmboe mode. Okay, so the question now is how does the transition occur? So, for example, are we going like this? For example, if we are just looking at the maximum growth rate, is it a continuous curve or not? Okay? And it's not. Okay? So the transition between the Kelvin-Helmholtz and the Holmboe instability is done like this. So here the black curve is the maximum growth rate curve. So, for example, if you start increasing j, you will see that there is a discontinuity here. And so what? So this means that the Kelvin-Helmholtz instabilities will be the first to be seen because it's the lowest Richardson number. And after there is a transition, okay, to less. This is not as strong as these ones, okay. And here these are the true Holmboe waves, okay. So one moving with speed given by this upper branch, and this moving in the opposite direction. Okay. And why have people looked to this special limit? Well, we already know that, you reduce from a quartic equation to a biquadratic form that is easily solved. But personally, I think it's not the only reason. I think actually this comes from the paper the results by Taylor and Goldstein in 1931, showing that, the difference between the Boussinesq and the non-Boussinesq fluids are negligible. Okay, so why to bother, right? The thing is that they have considered this situation. So they don't have 2 layers, but they have 3, okay? And since this transition layer here is the same as this vorticity layer, we only expect to see Kelvin-Helmholtz instabilities, okay? So, since we have a different configuration, maybe we should be more careful. So is it still the case here? If we increment, for example, if we enlarge our value of density increment, are we seeing still the same picture or not? And no, not really. So, for example, for 0.18, you see that the gap that existed in the Holmboe case between this Kelvin-Helmholtz mode and the Holmboe mode were really, there was a huge gap, right? Now it's closing, and eventually, around 0.2, it becomes a continuous curve, okay? And on top of that, for example, in this diagram, in the first one, there was no shaded region. Everything is white there, okay? Here you see this gray area, okay? This is something that cannot be captured by the Boussinesq limit. This means that you go from a region where there are 4 complex solutions to only 2. Here in the gray, there are only 2 real and 2 complex, okay? This is very important. So eventually, incrementing if you enlarge your epsilon, you see what? That eventually your maximum growth rate curve is completely included in this region, which means that if you were looking for Holmboe waves, you will never see it. Okay? So there is only one single propagating unstable mode. Okay, so we see that since it becomes continuous, one more problem is to identify, so it's not that easy to identify how the transition occurs. Okay, when can you say if it is still Kelvin-Helmholtz or Holmboe?
I didn't understand what you said at the end there. In this shaded region,
there are only
instead of 4,
2 complex and 2 real.
So
outside of these are the stability boundaries. So everything here is stable, stable.
Yeah, but so why won't you see it there?
Why?
You said you won't see it, the instability.
The counter-propagating waves, because you need 2 unstable.
Oh, you mean
So if you only
like Kelvin-Helmholtz. It looks like Kelvin-Helmholtz.
Yeah, this is the thing. I mean, it's not easy to... Is it still Kelvin-Helmholtz? This is the problem.
Okay.
There is only one unstable mode. But is it Kelvin-Helmholtz? Okay. So theory versus experiments. So this took more than 30 years, as I already mentioned. And this is a paper by Greg Lawrence, from 91. And they see what? They start from, for example, very low Richardson number up to very high. And they see what? They don't see the counter-propagating waves. They see what they called one-sided instability. Okay? So there is only one unstable mode propagating. And instead of building these billows, as the Kelvin-Helmholtz instability does, it's just a cusp. Okay? It never does this kind of role. It's just a cusp. Okay? It's quite different from the Kelvin-Helmholtz instabilities. Okay, but there's nowhere here 2 counter-propagating waves. And on top of that, let me just point out that their epsilon is 4 times 10 to the minus 4, which is very, very close to 0, okay? So which makes sense, I will say, to use Boussinesq approximation, right? Okay. Not only these things have been observed in labs, but for example, I took this picture from this paper, and people call this an arrested salt wedge. So whenever the rivers or streams are discharging to the ocean, so you see here the sea and the fresh water coming, you actually see 3 different regions. So here you see positive waves, what they call unstable, one single propagating wave going to the right. Here suddenly they change orientation, they start moving to the left. And here this will correspond to the ones that we know, the Kelvin-Helmholtz instabilities. Okay? And let me point out that these negative waves cannot be captured by the Boussinesq approximation. Okay, this is something that we realized after. So let me tell you how these experiments were being conducted at the time. So this is from 91, okay? And in this case, you don't have the counter-propagating waves. Okay, just the one single propagating mode with a cusp. Okay? So they were doing the following. So they will consider here a splitting plate between 2 different layers. And, well, at the end of this splitter plate, they will see what happens in this region. Okay? And what they have pointed out in their paper is that, well, maybe the reason we are not seeing the Holmboe waves, the 2 counter-propagating waves, and just one, may be related with this fact. So they see that the density interface is generally displaced with respect to the shear layer. Okay? And they pointed out, well, maybe this could affect the results. So we need a different model. Okay, it's very easy to change the model. So instead of putting the density interface at z equals 0, well, just bring it down a little bit by a small distance, d. Okay? So we'll have a new parameter, delta, d over h, and h is just this height here. We do exactly the same, and just look at the stability diagram and see how the things change. So, of course, the eigenvalue equation is still a quartic. The coefficients are slightly more complex. And let me point out that actually this delta is quite important because it's not that small. I mean, in their experience, for example, they were actually measuring things about 0.5 at the beginning of the splitter plate. After, in that experiment, along the channel, this delta will decrease, okay, but never vanish. This is very important. Okay, so this is the stability diagram and the growth rates, okay, that you actually see. So compare this with a non-displaced case. So the density increment is still the same, epsilon to the order of 10 to the minus 4. But just because we just just lowered the density interface with respect to the background, the inflection point of the background velocity, we got something completely different. For example, in this case, you see the following. Here is discontinuous, so there is a clear distinction between what is Kelvin-Hall modes and Holmboe. Here, well, where could we say that? I don't know. And on top of that, for example, in their experiments, Lawrence was looking for Holmboe waves here. There's no way, because, for example, here, there is only one single propagating unstable mode. You cannot have two. So I don't know how they missed this region, the gray one, but apparently they did, and they were not the only ones to do that. Okay? So one thing that you immediately realize is that, for example, here, in this case, in the white region, you have 4 complex solutions, which means 2 unstable modes. But look at the growth rates. This is a lot weaker than this one. So which means that, well, if they are not comparable, only one will manifestate. So you will see only one. Okay, so it's not surprising that in their experiments they were not seeing the 2 counter-propagating waves. Okay? Okay, but this is at the very beginning of the splitter plate. But what if we extend our experiment to later stage? So we'll be far away from the splitter plate, and our delta will decrease, never vanish, of course. So, for example, we have took 0.14 just to see there is something different, and here we realize the following. So here, this curve is pretty much included in the white region, which means 2 unstable modes, okay? But let's compare the growth rates. One is like this, and the other is like that. So, for example, if we will be looking for counter-propagating waves, well, somehow we will imagine that we should be close to here, because this is the point where the instabilities are more comparable, okay? So in order to manifestate at the same time, simultaneously, they should have strengths, comparable strengths, okay? So, I mean, maybe it will be possible to see these counter-propagating waves if they could tune this optimal Richardson number, okay? But we don't know about that. So, but finally, they were able to find those, and they found it by accident, okay? So they dropped using these mixing layer facilities, and they started to use exchange flows. And exchange flows, basically, we already saw, we have seen this yesterday. So basically, you have a container with a lighter fluid and a container with a heavier fluid, and you just lift the gate, okay? You cannot just lift it, because, I mean, you have to be careful. We want a subcritical flow in order to see upstream formation of waves, okay? So what we see here, this is the beginning, and this is when you lift the gate. You see the formation of very, very strong instabilities, Okay, so these are the Kelvin-Helmholtz instabilities. And later on, at a later stage, you see these things. And these are actually the Holmboe waves. And if you see a diagram with a delta, which is the displacement, you'll see that it will decrease from 0.4 up to 0.2. And from here, after t equals 1 second, they started to see these things, counter-propagating waves. Okay? Okay. So now, just to play with this, for example, assume that my delta is 0.2, and I want to see what are the difference by using Boussinesq approximation and not using it. Okay? So at 0.01, I don't see any big difference between the Boussinesq approximation and non-Boussinesq approximation. But if I have 10 to the minus 1, I already see a completely different picture. In particular, this curve, the maximum growth rate curve, is continuous and not here. On top of that, here I could only capture right-going waves, and here, as soon as I do this jump, these are left-going waves. Okay? And on top of that, I mean, you see that 0.2, I mean, your chance of getting true Holmboe waves are really reduced dramatically. Okay? But I mean, we were just trying to understand what are really the difference, and is this important? Okay? So at one point, we could see 0.1. So in order to see any significant difference, you have to push your epsilon up to 10 to the minus 1. Isn't this too large? I mean, based on their experiments, for example, Lawrence has used 10 to the minus 4, 10 to the minus 3, and Poulican, for example, and co-authors have used actually 0.06, 0.07, 0.08. And in all these cases, Boussinesq approximation has always been used. Okay? Okay, let me just play with delta. Let me decrease from 0.2 to 0.1. Okay. Here, I see difference for a lot sooner. So, for example, already for 0.045, I see completely different picture from this one. So this is epsilon equals 0, which means the Boussinesq limit. And this is what I could say it's a small epsilon. Okay? But you see that the difference are quite large. And for example, in principle, here, since these instabilities have comparable strengths, you will probably see counter-propagating waves, the Holmboe waves. But, for example, in a lab, you could be, for example, seeing completely different wavelengths for them because there is this discontinuity. Okay? And notice that this value, for example, is even less than the one used by Poulican. Okay, so we have reasons to imagine that if you discard, so if you are discarding part of the physics, so you are discarding the value of epsilon, the density increment, you could actually be seeing, I mean, you will be seeing, for example, Holmboe waves, but for example, you will be estimating their wavelengths and wave speeds in a very bad way. Okay? So this is something that we haven't found in a literature before, and well, we actually tried to push this thing, for example, in order to design lab experiments. So, for example, if I knew already that my delta will be 0.15, for example, what will be my two best fluids, for example, to use? For example, because in order to fit into the Holmboe case, people have been using epsilon very, very small. Okay? But, for example, here, this shows that, for example, it's not exactly the case. So if you want to minimize the difference between the growth rates of two unstable modes, for example, this is the correspondence. So for this particular delta, you should go here. This is the best possibility to find the Holmboe waves. Okay? So this idea that can be more easily observed for smaller values of epsilon is false. Okay?
Can I ask, what happens if, let's make delta 0 for the moment. Supposing the epsilon gets quite large, gets towards 1, so there's a huge density difference.
So you, the larger the delta, the later you will see the discrepancies.
Right, well, let's take delta equals 0 for a minute.
Okay.
Okay?
If its delta is 0, it's still the same case. You have to push up to 10 to the minus 1.
No, but could I make epsilon a half?
Yeah, sure.
Yes?
Yeah.
Can I see Holmboe way?
No. A half.
I'm too far.
Okay, let me point out this diagram. Okay, for example, imagine what happens here. So this is actually the relative difference between the strengths of two unstable modes. Delta, if increases, I will see that the difference is increasing. So for example, 0.5, I will see that even if there are two unstable modes, they have completely different strengths. So probably only one is showing up. So you have to go down. And around 0.2, here, for example, people already observed this. Okay? But in order to see discrepancies, you should be here somewhere. For very small epsilon, it immediately shows a discrepancy. For example, instead of seeing a continuous curve for the maximum growth rate, you are seeing discontinuities. And jumps from right-going waves to left-going waves and things like that were never observed before. Okay? So I think I will end here. Thank you.